So in this course, we will be discussing mainly the small molecules only. So let us look at VSEPR theory, because applying VSEPR theory to large molecules are going to be extremely difficult. So we will be just restricting ourselves when we study about VSEPR theory to small molecules and ions only. It is basically an observational model, and the molecular formula cannot be used to predict the structure, geometry or the shape. And this assumes that each atom in a molecule will achieve a geometry that minimizes the repulsion. So this is the most important thing about the valence shell electron pair repulsion. So we talk about repulsion here as a major cause which is responsible for that particular geometry of that molecule. So basically the electron repulsion happens in the valence shell only. So this is the major crux of the VSEPR theory. So we have three types of electron repulsions that may exist in a molecule. The first one is lone pair repulsion. The next one is lone pair bonding pair repulsion, and the other one is bonding pair repulsion. Magnitude wise, if we are looking at the repulsion, the lone pair repulsion is having the maximum magnitude, followed by lone pair and the bonding pair. The bonding pair repulsions are very minimal, and this repulsion actually exerted by the bond pair decreases with increasing the electronegativity of the ligand. That means when we talk about two atoms which are connected by a bond having large electronegativity difference, then the repulsion exerted between the bonding pair will be very minimal, because one of the most electronegative atom tend to keep the electron towards itself for majority of the time. So the bonding pair repulsions are going to be minimal in that case. And when we talk about multiple bonds, they repel more strongly than a single bond. So these are all the various aspects of the VSEPR theory. So when we make the VSEPR theory, we actually have a couple of assumptions. That means electrons are not point charges, but they form charge cloud, and the bonding pair of electrons remain between the atoms. The lone pair of electrons on the atom is spread in space. So these are some of the assumptions which we are actually having while we are trying to explain the VSEPR theory. Sir, you said electron repel each other, then why there is no repulsion between two electrons in the bond or in lone pairs? Yeah, it's a very good question. See, there are a couple of confusions people have. The first one is, when we talk about the repulsion, what we are talking is not the electrostatic repulsion, but we are talking about the Pauli's exclusion principle. So this is the major difference you have to keep in mind. When we say repulsion in the VSEPR theory, we are not talking about the electrostatic repulsion, but we are talking about the repulsion according to Pauli's exclusion principle only. So what is this Pauli's exclusion principle? So according to this principle, orbitals are orthogonal. So in other words, orbitals are perpendicular to each other. So but it does not say anything about how electrons will occupy in a 3D space. So that is what is the major thing, because the VSEPR theory is based mainly on this Pauli's exclusion principle only. So we cannot employ this for electrons which are occupying three-dimensional space. And we are also completely ignoring the nuclear electron attraction, which is extremely important, and we are also completely ignoring the nuclear repulsion, which is also very powerful. So these are some of the limitations when we apply VSEPR theory. So you have to pay attention when we are applying VSEPR theory to large molecules. Let us start with the VSEPR theory's application. We know carbon dioxide molecule is linear. This could be explained very easily by the VSEPR theory, because if you look at the structure here, the carbon is in the center, because we know carbon is more electropositive compared to oxygen according to the Lewis dot structure. So the oxygens are put at the extreme end, then we have actually the linear structure. In this linear form, the lone pair electrons are the minimum one. So that is the reason carbon dioxide takes a linear shape. So that could be explained very easily by VSEPR theory. But when we go to the water molecule, we can simply extend the carbon dioxide to the water molecule also, But unfortunately, in the case we have a central oxygen, here there are two lone pairs on the oxygen, they repel each other, due to which the molecule is actually having the bend structure. So here we have a lone pair bonding pair repulsion. So due to which the molecule, the water molecule, is actually having a bent structure. This also could be explained very easily by the VSEPR theory. So these are some of the applications which were actually true according to the VSEPR theory and the actual structure of the molecule. Let us look at a little bit complicated structure, NO2, NO2 minus and NO2 plus. Can we predict the structure using the VSEPR theory? Now, before we get into that, let us look at the number of valence electrons. The nitrogen has 5 valence electrons and oxygen has 6 valence electrons. So this again is a triatomic molecule. CO2 is a triatomic molecule, water is a triatomic molecule, NO2, NO2 minus or NO2 plus, all these are basically triatomic in nature. So that means we know two structures which are possible in the triatomic already. One is a linear structure, another one is a bent structure. If we extend the same, maybe the NO2 may have a linear structure or it may have a bent structure. We don't know, we have to actually figure it out. And let us look at what the VSEPR theory talks about these molecules. Now we have written the Lewis dot structure here. NO2 is written here as shown here because the nitrogen is having one odd electron, and in the case of NO2 minus we have actually the nitrogen with the octet configuration, and in the case of NO2 the nitrogen is also having octet configuration. So these are the different structures for the three species. And if you look at the bonding pair on the nitrogen, the NO2 has 3 bonding pair and 0 lone pair. And in the case of NO2 minus, we have 3 bonding pair on nitrogen and 1 lone pair. And in the case of NO2 plus, we have 4 bonding pair and 0 lone pair on nitrogen. So these are the Lewis dot structures. You can read the e-textbook for how to get the structures for all these 3 species. Now, if we extend that, in the case of NO2 molecule, what we have is there is one single electrons on the nitrogen. So there is going to be a little bit repulsion between this electron and the bonding pair. So that is the reason it is going to have a small bent shape, because if we go back to the water molecule, there are 2 electrons on the central oxygen. So that is the reason there is a strong repulsion between the lone pair on oxygen and the bonding pair. So water molecules also having a bent structure, but the bond angle was very low compared to the NO2 here, because here the bond angle is 134 degree. So that means the repulsion from this lone pair, this lone electron and the bonding electron is not very high. When we go to the NO2 minus, there are 2 electrons, that is there is a lone pair on the nitrogen. So there is going to be more repulsion between the lone pair on nitrogen and the bonding pair, due to which the molecule takes a bent shape. Here the angle ONO angle is 115 degree. So you can see the difference according to the VSEPR theory. The repulsion on NO2 is lower compared to the repulsion on NO2 minus. So that is the reason there is a difference in the bond angle. And when we go to NO2 molecule, there is 0 lone pair on the nitrogen. So that means there is no repulsion possible on this particular case between the lone pair and the bonding pair. So this is very similar to carbon dioxide molecule, that is a linear one. So the bond angle here is 180 degree. So using the VSEPR theory, we can actually explain the geometry of NO2, NO2 minus and NO2 plus in a very simple way, and this exactly matches with the experimental observation also. So VSEPR theory is actually useful in explaining the structure or the geometry of very small molecules. Finally, let us look at some of the limitations of the VSEPR theory. It fails to correctly describe the electron geometry of water. Of course, we know there is a lone pair repulsion on the water molecule, but the VSEPR theory treats both the lone pairs in the equivalent way, but unfortunately they are not equivalent. So the electron geometry of water could not be explained by VSEPR theory, and the molecular geometry of thiols, disulfides and peroxides could not be explained by VSEPR theory, and even the electron and the molecular geometry of aldehydes, ketone, carboxylic acid derivatives, organic halides, etc. could not be explained, and many metal complexes could not be explained using VSEPR theory. So these are the main limitations of the VSEPR theory. Why this limitation is because the VSEPR theory completely ignores the orbital mixing, because in the recent molecular orbital theory explanation, we will be using orbital mixing to explain the geometry of the molecule, but VSEPR theory does not talk about orbital mixing, and pi conjugation is also not considered while we talk about the VSEPR theory. Dipole-dipole interactions are never considered, and hydrogen bonding is also not considered. So these are some of the reasons why VSEPR theory fails in the case of organic compounds, especially which are large molecules.